it's really a pleasure to speak on time series analysis, which I was working on some time back, starting from chaotic analysis of chaotic time series. So I'll be talking on time series analysis in general, and including linear time series analysis, nonlinear time series analysis, and then there's some of the recent trends. Okay, so main thing I want to focus on here, like, I know there are a lot of freshers here. So for their convenience, for their benefit, I will also show some, I will show some demonstration, like how to calculate all this, because to board the young minds also, like, to this topic. So, some of the recent trends I will be talking, and some of the research problems which I will also be speaking on. So basically, it's a bit of kind of demonstration and our work, and what we can do with the time series analysis. Some of the tools you can, you should be familiar with, and a bit of a general thing, and some of our work we will be showing it. As Professor Shankar Raman has said, we were also working together on some of the experimental time series, like, so time series you can see almost everywhere, like almost all experimental setup, natural time series. It doesn't restrict to science or engineering. Even social science, you will be dealing with a lot of science time series, like economic time series, share market, and other things. So this will be a bit of a general tool to get the underlying dynamics. How can you get the underlying dynamics by just analyzing on time series? That is what we'll be speaking more. And some of the chaotic dynamics I will not be talking much, but I will just go through it actually. Okay. Thank you for a kind introduction. I'll be talking on this actually. So let me first ask you: my PPT is visible to you all? Is the screen visible?
Yes, sir. Yes, sir.
Oh.
This is visible.
Okay. Yeah. Thank you. So the content of content of my talk is something like this. Like, first, I'll be speaking on linear time series analysis. I'll be particularly concentrating moving average, ARMA model, ARIMA model, and even I will show you how to get this model, like how to do that. Because these days there are a lot of software packages, tools. So even if you're not very good in programming, computing, and with all these softwares, it's a bit easy. Like, these days people are getting these results just a few clicks away. Like, if you're capable of clicking at the right icons in the software, it will give most of the results. Like, but only thing you should know the underlying physics or the underlying theory to interpret the result. Like, but what I wanted to convey is that you don't have to have a very deep knowledge in computer programming, anything, but there were times that for everything you had to write your code from the scratch. But these days there are a lot of good software packages. I'll introduce some of them. And first I'll be talking about linear time series, but just a brief one, because mostly in science and engineering we'll be dealing with the nonlinear time series analysis. I'll speak on the basic concepts and how to get this. I'll also show some of the software, like a Tyson Package time series analysis package. It's one of the popular and very good software, to my knowledge, on analyzing nonlinear time series. And it is easy. Bit like command like a software, but there are these days you have an GUI in R actually for something called the R Tyson. That also you can use. And some of our research work papers, if you are interested, if I have time permits, I will write from the beginning how did we do one research paper to get an idea. Like, if you want to analyze one particular time series of your interest, sometimes you may have one time series of how to analyze right from the scratch to what you can do with these softwares. If time permits, I will do that. Otherwise, I will just go through the main aspects of the paper. And if, at the end of the discussion, if you are interested, I'll be speaking on how to do that actually in practically, like a demonstration, how to get all those figures, how we can do. Because why I wanted to say this is, even without much deeper computer knowledge, you can do this kind of thing because of the packages. That's what I want. The recent trends in analyzing time series is to convert into networks. Network, or the mathematicians call it as graph theory, or graphs, is totally a different mathematical object. But these days, people analyze time series using network. So I'll be a bit talking about this, and it's an emerging trend, and a lot of work is going on in that direction also. You can construct different kinds of networks from a time series. So by analyzing the network, you will get the dynamic characteristics, the structural properties, and other properties of the time series that you will get just by constructing this network. The constructing this network is also not that difficult. I mean, you have to analyze, but it is still emerging, and network, actually, you may not be getting all the dynamical quantities, but the structural quantities like attractor diversion, and you can get from the networks, but it's still emerging. We are also working on these networks. Apart from the time series to network, we are also generally working on complex network analysis. But this is one area where we can convert the time series into network. And there are reverse processes also, from the network you can get to time series, etc. And this is what the general idea about that. Recurrent networks are very popular these days in for analyzing nonlinear time series analysis. And there are several other kinds of networks also which we can calculate. So I will be showing bit kind of this, and what I wanted to say is I'll introduce all the concepts with the physics behind it, but at the same time it's a bit of kind of a workshop like demonstration also, because most of the youngsters, I mean, otherwise if you talk very high of the ideas and may not be that practically useful. So I mean, I just wanted to show that this is not very difficult actually. So this is the plan of the talk today, and I'll be moving from linear to nonlinear and the networks one by one. But I won't be spending much time on linear time series analysis because it's well established, and most of the time series we have is are nonlinear. So what's a time series? Time series is some kinds of measurements equidistant in time, in the sense you measure some quantity. Say, for example, you measure the temperature outside your room at every 1 hour, a fixed time interval. If you measure, you get a time series actually. Say, for example, you measure the temperature at every 10 minutes, not 10 in the morning, 10:10, 10:20, 10:30, every 10 minutes interval. If you measure, you get quantities. So this is what called the time series. No, it is a series of values measured at mostly the time interval is almost equal. Then you call it as a time series. It occurs in almost all branches of science, engineering, not only in these, even in social science, and where not, almost everywhere, it is all, you can say it is ubiquitous time series. So the question is, now, can we infer some useful information by just looking at the time series and get to know what's the underlying dynamics, whether we can get the physics out of it just by looking at the time series? So that would be, we are more interested. I just wanted to get a feeling about the time series. I am showing some of the time series mostly related to physics or science actually. On the right top corner, this one is actually, so this one is Earth magnetic field. If you measure the magnetic field, that is also fluctuating. If you look at it, it's just almost like random. Is there any dynamics behind it? Whether the dynamics is deterministic or just stochastic, random fluctuations. I mean, can you see that whether you can predict the next value by just looking at the time series? So that is what is a bit interesting in that aspect. If you can predict it, if you can get to know what are the parameters involved in the evolution of this magnetic field, etc. But we don't have a differential equation as such. And this one is total electron content. If you measure the total electron content per square centimeter over the Earth's surface, right from the top, mostly the ions are present in the ionosphere. If you can measure that kind of total electron content, you'll get a time series. It's also randomly fluctuating. And see, so this much fluctuation is whether you can get to know anything about that. This is also very relevant in space physics. Not only that, technologically also, because it depends upon, suppose if you want to transmit shortwave radio and all, it very much depends upon the ionosphere. If the ionospheric dynamics and ionospheric fluctuations, the total electron content and all is very much related to that actually. When it happens like magnetic storms in the outer space, how does it affect the total electron content? But many times, many of the parameters, many of the physics behind it may not be amenable to analyze, but we have this time series actually. From this time series, can we infer something out of it? That's what we are interested. Most simple thing is like a periodic a periodic time series, something like this. Okay, here this one is very periodic, like, you know, almost it's very simple one. By just looking at, you will get a lot of idea about the dynamics behind it. But just when it is very simple, like. But most of the times is particularly the naturally occurring time series, not the measurements, not the time series you measure out of some experiment or generating from some equipment in the laboratory, or even mathematically from the differential equation. It's not that about. The naturally occurring time series is very complex. And just by looking at the simple tools, you may not get any idea what would be the physics behind it, what would be the dynamics behind it, like. And this one is total number of air passengers in terms of lakhs. I mean, the number of air passengers is slowly increasing, like, you know, it has got a periodicity, like, you know, passengers travel most in the December, that kind of area. So it has got some kind of periodic behavior also, like, you know, it is ever increasing, like slowly increasing this time series, like, and that is total number of passengers. So this is another kind of time series. So, and there are a lot of economic time series. Even if you measure that share value, like, you know, at every day, the closing price of a particular share, and then you get a time series, it is almost occurring. To get a feeling about that is something like this. These are the measurements. No, this is time series, like, you know, first value, second value, third value, like that. Here, the first value is just so. A time series only this much, actually, this much looking like a time series. Okay, these are measurements. So we only have this. And sometimes we are lucky that we know the physics behind it. We know a differential equation, or physics, we know the system. Like, you know, for mathematicians, they call it as a differential equation. But for physics, we can say we know the system. So many times we know the system, but many times we don't know the system. Like, we only have the measurements. So if we know the system, we are lucky enough because we can analyze it. We'll get a more idea, like, about the physics behind it. And even simple map, like, you know, if you look at it, this is a simple map. So the value of x naught, you can say x naught at the point. So then you will get the x1, then x2, like that. If you keep on putting this, you will get a time series. Like, you know, it's a very simple map, and this is known as logistic map. And it is demonstrated that the dynamics of this series can be very, very complex. Like, you know, yeah, as a system, it is very simple, but the time series it is generating can be very complex, from a simple constant solution to periodic solution, and a lot, actually. So, I mean, just by looking at the differential equation, you may think that it's very simple and the behavior may be simple. But at a particular parameter value, as the parameter changes, this can be very complex, and you can demonstrate very complex solutions. Like, so that is what I wanted to say. Okay, so the main message here in this slide is that there are different types of time series occurring in physics, something in laboratory, something outside the laboratory, and in social science, engineering, almost everywhere time series are there, like, you know. And another thing is that sometimes we know the physics behind it, we know the differential equations governing the system, but many times we don't have the luxury of having the differential equation. Many systems have not been modeled already, like, you know. So in that situation, what we can do, like, you know, that is mostly about the time series analysis, like. So this is what I wanted to say at the outset, like. And can we predict the future values of these irregular fluctuating quantities? Many times these quantities are fluctuating irregularly, like, you know, it's looking like a stochastic or random behavior, like, you know, whether we can predict it, or is it really stochastic, or is there any underlying dynamics behind these fluctuations? That is what we want to analyze, all those things. I mean, many of these questions it has got an affirmative answer just by using the tools of this time series analysis. And whether we can, if we are capable of model these kind of fluctuations, deterministic or stochastic. I mean, these are entirely two different worlds. You know, with the stochastic behavior, you may be to the extent you may predict the average value or the expected value. Beyond that, you may not be able to predict much. But with the deterministic system, I mean, you know, there is a rule governing this system. So if you know the rule, you could predict the future values. But in the chaotic, at least, I mean, you can predict at least a short-term prediction is possible very accurately, like. This prediction was very, it's not a very new idea, like, you know, and it's an old idea, like people started predicting season and other thing, season and other. And long back, it was an interesting subject for many people, like, you know. So if you want to say application, it's almost all areas of science, engineering, social science, as I said. I mean, it's got a lot of application, medical science, military. I mean, it's just to name a few, like, it's a very long list. And examples of time series is weather data, climate data, tide level, seismic waves, like, and sunspot numbers, financial markets, EEG in biology, like, so I mean, the medical science, there are a lot actually. So you might have recently heard that the El Nino behavior, I mean, it's in the other part of the world, but that affects the monsoon in Kerala also, El Nino. So El Nino has a time series, like that is a sea under current. So how that occurs, that has got an effect in the in the monsoon season in Kerala, like. But what we have is only the time series there, like, we may not have the exact differential equation, but we want to analyze that and get an answer. So basically, a linear system usually model the local subsystems, like, a system may have very complex, very components, like, mostly these linear analysis restricted to component kind of things in the subsystems, like, that is what generally people do with that, to identify season, trend, cycles, outliers. These are some of the applications of linear time series, but I will be going through that briefly, shortly. And mostly I'll be speaking on nonlinear time series analysis and introduce some of the tools also, like. So nonlinear techniques exploit the measurement data and computer power. You need to have a bit more computing power to do the analysis, like, but these days it's not a question, it's not a problem, because you have very, very, very good computers these days. The computing power is not a limit actually. And you can just even get a similar dynamics just by looking at the time series, or just by analyzing the time series. You could extract a dynamics which is almost mimicking the original dynamics. That's the beauty of it, like, better than usually this nonlinear analysis, time series analysis, the result will be much better than the linear analysis. The linear, if it, I mean, as the word says, only like trend, I mean, it's a short-term prediction, but many things in the world are not linear. Like, usually with the linear analysis, you may do kind of moving average, ARMA model, ARIMA model, even you may find autocorrelation, Theorem analysis, these kind of things, like. But in nonlinear, you will reconstruct this state space. I mean, you reconstruct the attractor. So, but with that with one quantity, not with all the components of the system. Like, then you may calculate correlation, dimension, Lyapunov exponent, whether it is chaotic to know whether it is chaotic or not, and whether to check whether the given time series, it may look like a stochastic, but in reality it might not. So how do you know that the time series is stochastic, really random fluctuation, or is it has got some kind of dynamical behavior, like, there is a rule governing it. I mean, to know that there is something called a surrogate data test, you can do that to get an idea whether it is rising out of linear noise, like, there are a lot of tools for this. First, we will be talking about linear methods, some of the linear methods like moving average, ARIMA, and ARMA. So just to get an idea about this one. Moving average, see, for example, on the left panel, you have blue lines. That's a time series, like, moving average. Sorry, the real time series. But it's almost fluctuating, like, you can average. Every value is replaced with the average of the neighboring values. I mean, including the fourth, like, so you can make a bit of averaging. When you average it, you will smoothen the time series, like, that will give an idea, like, it will give some kind of better idea than the original time series. So that's why it came into something like moving average. If you look at the right side, it is the Florida daily COVID-19 deaths. The COVID-19 deaths in Florida state, like, if you look at the original time series, like, the blue time series behind, I mean, it's almost fluctuating. You wouldn't know whether it is increasing or decreasing or stagnating, like, kind of situation. You may not get a better idea, like. So the red one is a moving average. Moving average means every value is replaced with the average of the 7-day values, like, including that particular value. 3 values behind, 3 values on the ahead, and that value. So you have 7 values. You find the average of that, and you replace every value with that, actually. So if you look at it on this one, the red curve is more revealing, more revealing, in the sense initially it is increasing, then it is bit kind of stagnating, I mean, decreasing. We get a more better idea of the time series. That's why it came kind of moving average. That is what moving average is. Very simple concept thing, but it's useful in many situations, like. to get the trend or the well. So auto-regressive. Regression means you write it as a linear combination of the values. Like, here we call it as auto-regression because every value is written as a combination of its previous values. Like, we want to find the coefficients and the error we want to minimize. So this is actually the auto-regression. Why auto? Auto because you are writing its own values, its previous values. So we call it as an auto-regression. Moving average is kind of bit unnecessary fluctuation. It will kind of cut off, like, it will reduce the unnecessary fluctuation. So you get a moving average model, then you fit into autoregressive model, then you have autoregressive moving average model, like an autoregressive moving average model. It's a combination of this. So every value is written as a combination. Now we have two parameters. That is what I wanted to say. Like, in the moving average, you average over Q number of values. Whether you want to average over the 3 values, 4 values, so there is a parameter here that you have to decide. Like, the Q value. The Q comes from the moving average. Then regression after how many previous values you are going to take for write the linear combination. Like, how many previous values. So there are another parameter. So ARMA has got 2 parameters, P and Q. For the right choice of the P and Q, you may get a lot of good. You may get a good model. Like, but these days computer packages will find the best one, the optimum one. That I will show you how to do that also in the process. Okay, so this is what ARMA model. But the problem many times is this: many kinds of theory, even the nonlinear time series, and many of the tools assume that the time series is stationary. Stationary means the probability of, say, for example, if I want to see the price of gold, 1 gram of gold in 1960 and now in 2020, like, what is the probability that in one day the price will increase to 100 rupees? 100 rupees increase. What is the probability that the price of gold will increase 100 rupees in one day? Like, that you calculate in 1960 and you calculate in 2020. But here the probability is not the same. Like, so in a time duration, what is the probability of increasing a particular quantity? That depends upon the time. Then it is non-stationary. If it does not depend upon the time, it is stationary. In the sense, the probability of increasing 100 rupees same here in 1960 and 2020 means it's stationary. Like, that depends upon the time. Across the time, if the probability is constant, then we call it as a stationary process. If it is not constant, we call it as a non-stationary. And many times it is as non-stationary also. So, one point I want to say here is most of the analysis for stationary. So in these cases, what people used to do is they will convert this non-stationary time series into stationary time series and then do the analysis. One way of doing this to convert into stationary process to find the difference. Like, you have a time series, you have first value, second value, like that actually. So find the difference of first and second, and then find the difference of second and third. Like, then you have a series of differences. Then that might be stationary. If that is not stationary, again find the difference of that differences. Like, this is the process people usually do to make it stationary. Once you have a model for these differences, then you can go back to the model of the original time series. That is what we do. So here you want to make the difference. Then you have one more parameter, like, D. So ARIMA, this is what they call the integrative model. Like, so this D want to find how many steps you want to kind of make differences, find the differences. So there is one more parameter. So this is the full, in a way, is a complete model for a linear analysis like ARIMA. Autoregressive integrative moving average model. So it has got 3 parameters. One is for finding the average, how much values should be averaged over, and the P is for the autoregressive, how much previous values you want to find, and D stands for the autoregressive the differencing. Like, so these 3 parameters, once you get, you can find the model. So I'll just show a bit of demonstration to get an idea. Like, it's not that difficult. You all know about the R program. R has got this. R has got this packages. Most of the packages have R. Let me show you actually, because then it will be more useful. Like, I hope you can see this. You can see my screen. Like, So just there is a package, and you might have heard of R. R is a statistical data analytic package. So they can do this in R actually, because of these parameters, it's not that difficult to practically do practically. The first thing is there is a package called forecast. So if you install this package, you have to load it actually. So I mean, how do you load this package? In R, there is a simple command like kind of library forecast. You have to first install it, and then so, and I mean the data is also there, like in air passengers, like air passengers. That data is there. If you look at it, the data, you get an idea kind of. This is the air passengers data from 1950 to 1960. Like it's slowly increasing, and at the same time it has got a seasonal effects and all. Usually, if you want to kind of get an idea about the components and all, before going to the ARIMA analysis, if you want to get a kind of component, then you can do that actually, because these packages are very good in that, these kind of things actually. So see, if you say that decompose this one, it will decompose into several one, like this will get the overall trend. This is the original time series, and this is the original time series. Then the overall trend, how it is increasing, like so it is a moving, you get the trend. Then it is kind of fluctuating, like it has got a seasonal effect. So this is the seasonal effect of it. And other residues, like a random, it has got a bit of random numbers also. Why? Because random, because every measurement will have some kind of measurement noise, like in every data. Like. So this is kind of this one. So now we want to model it actually. So how do you model it? In this package, if you want to model it, the command is something like auto ARIMA. So the auto ARIMA will fit these P, Q, D values, and you don't have to specify it. It will take the best one. So this is as simple as that, and it will model it, and the model is saved into the word model. So this parameter will have that kind of, it will give all kinds of values. So each parameter it will give, and suppose if you want to plot it now, so just want to plot this actually, this forecast. Okay, so if you look at it, so even you can predict it actually. See how, I mean, only up to 60 we have data. Now we predicted it to more data, like almost 5 years we have predicted ahead. I mean, it's, by looking at it's a reliable quantity, like the darker blue is the prediction, but it can vary across this much. I mean, the prediction may not be perfect, like it can vary around the shaded region. Like getting this figure is so easy. Why I showed these commands is just for the freshers and to show that this is not very difficult. This analysis is not very difficult. I just wanted to give that you only have to identify the right package. Like in R, you have most of the packages for this kind of analysis. So it's a linear system analysis. Okay, so now we'll move on to nonlinear time series analysis. More nonlinear time series analysis. I mean, this is one of the famous chaotic system, like Edward Lawrence, and so it's a bit of a convention model actually. How heat transfers, like So I mean, if you give the initial condition for X, Y, and Z, there are three variables. Like they are a coupled system in the sense, and X in the here or Y here will affect this one. If this equation has only X and this has only Y and this has only Z, then it is decoupled actually. But here it is coupled. The variation of one quantity will affect the variation of the other quantity. It is there, like by looking at it's a simple differential equation. But if you integrate X, Y, Z is integrated. See, this is very complex behavior, like very complex behavior it has got as time goes on. And another point I wanted to say, this is a chaotic system. Chaotic system in the sense, a small difference in the initial condition will exponentially diverge. Like if you can integrate, you can get the values also, like X, Y, Z. Now, if you want to get the attractor, we know all the variables, like X we know, Y we know, Z we know, all the variables we know. So once you know all the variables, it is easy to analyze, like in this system. But many times that may not be possible, like Edward Lawrence introduced this in almost in the 60s, like as an accident. He invented the chaos accidentally, in the sense at that time the computers were not that fast, and he integrated this for 1 day and kept, for numerical interaction, kept it for 1 day, and then switched off the computer, not up to the last values. Then the next day he started off with the last values of the previous day as an initial condition. So when he repeated this experiment several times, there is a huge difference. Then only he realized that then a small difference can exponentially diverge. That is what we call the chaotic system, and people say that this behavior is called the butterfly effect. In the sense, this atmospheric system are chaotic because a small disturbance in the atmosphere can change, can have a huge impact later on after a decade or something. Yeah, even if a butterfly flaps, that will make us very small disturbance to the atmosphere. That can become a tornado later in some other part of the world. That is what popularly known as the butterfly effect. See. Okay, so that is what called the butterfly effect. Okay, and this equation you can get the attractor. Attractor in the sense this is x. You can say this is y, and then you can plot this time series. You'll get an attractor. Attractor in the sense, even if you start with some other places, it will finally come to this, and then ever it will only be rotating within this. This is called an attractor. If you think of the simple pendulum, very simple pendulum, if you start with 30 degree, the pendulum will come to the equilibrium point like 0 degree, like that is the attractor. So once it reaches there, it won't move away from that equilibrium. But in many cases, these attractors are very complex, and you might have heard of like a strange attractors, like its geometry is not of ordinary regular geometry. It will have very strange complex geometrical behavior, like. So, but why time series analysis, when we know this differential equation, okay, so we can integrate, we know all the x, y, z component, we can plot like, like the attractor you can construct. But many times we do not have the luxury of this differential equation. There is no model available. Say, for example, temperature, if you take every hour, if you measure the temperature in Celsius, you have a time series. But you don't know what are the parameters it is affecting here. But here, x is affected by y, right? It is, even if you know the equation, y is affected by z, and you know which affects which, and every variable is affected by every other variable in the system because it is coupled. You know the system, but in this case, you do not know the system, like you only have temperature. And that might be affected by very other variables. You don't have a differential equation like this. By just looking at this, actually, by just analyzing this temperature series, whether you can get some kind of inference, at least some glimpse into the underlying dynamics. That is what we are trying to do with the nonlinear time series analysis. Another example is wind speed. The speed of the wind at every 10 minutes or something. This has got an atmospheric science. This has got a lot of importance. Apart from that, the wind speed time series analysis has become very popular these days because of the wind energy, because of its application in wind energy. Wind is a clean, it's a clean energy source, actually, renewable energy source, clean renewable energy source. So, but if you connect this wind energy generator with a grid, actually, you want to know whether there will be wind after some time. Like, if there is no wind after 1 hour, then you may not be able to produce any energy from that. Then you have to have a spin energy reserve, like spinning reserve, some other source to provide that. That spinning reserve is very costly these days to maintain, actually. So they want to know whether you can predict wind ahead. There are a lot of methods now. It's become an emerging area in the renewable energy sector because wind is very clean and want to predict, actually. People have started with the ARMA model. Then there were a lot of deep learning and machine learning techniques, neural networks, all kinds of if you search the literature, you will find numerous number of methods and their applications, and a lot of papers, like lot of papers on wind energy because of his engineering application, right? So you want to predict it, actually. So this is one of the area we were also working, like, we were also analyzing this. And initially, this is assumed to be fluctuating. Like, they thought it is stochastic, and they were predicting it as a stochastic time series. Like, then we demonstrated, then we showed, our analysis showed that it has got a determinism, and the short-term prediction is very accurately, very accurate. We can make very accurate short-term prediction with these tools, actually. That is what one of our area. All this, like nonlinear time series analysis, everything is based on the Taken's theorem. Right? Taken's theorem and the Flores-Taken's analysis, and he showed that even if you know only one parameter, one time series, you can construct the entire time series. How many parameters are affecting it, and you can get the attractor topologically equivalent. He mathematically proved it actually. Say for example, in the previous slide, we saw that even if even if you only have X series, we do not know this on Y, and Z also the time series we do not know. We only know X. If we give this X time series alone, we can construct the attractor as in the previous case. That is what he guaranteed. He proved it mathematically. He proved it mathematically, like you can do that. That is what popularly known as Taken's theorem, Taken's embedding theorem, like So, and then there was something called a further on that. He showed it for the map, say, discrete map. Then this paper in 1991, they say that even for continuous system, and we can do that. This is one of the source for the development of this, all the methodology, tools, everything on this particular paper. Okay, embeddology, like, okay. So even, and when you do the analysis, many times data may not be cleaning. Then sometimes the dimension will be large, like, the earlier differential equation I saw, the dimension was 3. Sometimes in real system, the dimension is very large. Even if it is deterministic and the embedding dimension is very large, if it is a higher dimensional system, it may not be that useful. Like, it is almost as useless as a stochastic time series. So, for a stochastic random time series, the dimension is almost infinite. Like, you can never predict it. It's not a low dimensional system. But if it is low dimensional, the prediction it will be more accurate and it's very convenient. So we will always go to check whether the system is this one. So to integrate, there are two parameters. One is called the delay. I will explain what delay means actually, and then there is something called the embedding dimension. So if you know this kind of delay, tau or d, if you represent, then the embedding dimension we will represent it as m. So if we know these two parameters, we can reconstruct the time series. I will show how we can do that actually. So delay means if you have a time series of every 10 minutes data, like, you may not be using the one. So you take the first one and then take a delay. You may take only the 4th value, then maybe 8th value, 12th value, like that. You may delay it, like, so how much delay? See, for example, every value you may not use it. For an optimum delay, you can predict it. Delay. So I said to embed, there are two parameters. One is embedding dimension. I'll show you. I'll demonstrate with one data set, and if the delay is too small, either when you reconstruct it may not be faithful. So a correct one, if the delay is an optimum one, you'll get a better. It's almost equal to the original system, like, So if it is too large, also it is not good actually. It is not good if the delay is too large. It's so you need to find an optimum delay. There are methods for that. So this is a time series, right? This is a time series blood pressure signal. So it's a blood pressure signal. So if you look at it, you may think that it is random, but if it is embedded into a system, but this one is with a very small delay, it's a better delay. So you get kind of a shape, like, So it has got a shape means you can get the attractor. It's too large is also not good. And another thing they want to say that if there is a fundamental frequency in the time series, you should not use that as a time series. Then again, it will give kind of artifacts. So that is one parameter. And how do you get it actually? The popular method these days to get the design, this one is mutual information. I'll explain that also, what is mutual information. So you want to get a kind of mutual information. So based on mutual information, you can do that actually. So what is mutual information? Mutual information means it's a statistical kind of thing, a probability based one. So suppose you have two time series. Can you predict the value of one time series by looking at the other one? In other ways, whether the second one carry some kind of information from the first one, like, say for example, wind and temperature. If wind and temperature coupled, like, if wind increases, temperature may go down or something. If it is coupled, then you may be able to, if that is true, you may be able to predict the temperature by looking at wind actually. So kind of whether you can find the information of one time series by looking at the other one. So this is what they say that, something like mutual information. So mutual information, you can use that and find out. Another thing is autocorrelation. Autocorrelation, how it is correlated with the previous values. And I have already said about correlation, how the present value is correlated with the future values. If you find that these kind of things, here I'll show you one example. This is from an original time series, like total electron content. So this is one is from this circular one is mutual information. This is mutual information, delayed mutual information. Say, for example, you have 100 values as a time series. You take the first value up to 99th value. So you get one time series. Then you have the next time series starting with its second value to 100. So one time series is split into two, not split into two, you convert it into two time series. First to the first to the 99th value. So that is one. Second to 100 value, you get a two time series. Then you find that these time series has got kind of mutual information. From one to the other one, you can find the mutual information. Mutual information from the information theory is based on statistics, actually. So then one delay means, so the delay is one, like delay is one. Then you take first to 98th value, up to that you make it as a time series. Then you take the third to 100 or something. So what you get is actually, then again, so you delayed it. The difference is first two values you have removed actually to make a second one. So then the delay is 2. Then again, you find mutual information. If you keep on finding that as the time increases, because the present value may depend on the previous value, but the long past it may not depend. So the mutual information will slowly decrease actually. So usually what people do is where the first minimum occurs, there you take actually as the delay, proper delay. So if it is too large also, theoretically there is no problem. Computers, it will create much problem. So the optimum delay is somewhere around here. This value you can take, but there is no in the sense of mathematically precise value for that. Even if you take some values in between, you can faithfully reconstruct the attractor. So you can either use autocorrelation or mutual information. But anyway, mutual information better quantity for finding the autocorrelation. Then you want to construct an embedding dimensions, because in time series you only have one dimension now. Say for wind time series, you take only wind, but the wind may be affected by humidity, temperature, or so many other values but you wouldn't know which are the other parameters affecting it. So how many dimensions the underlying system has got? Because this wind is evolved not as an independent quantity, it may be affected by so many, the internal dynamics of the earth, who knows, or the atmospheric temperature, because wind occurs due to the fluctuation in the temperature, but there may be so many other parameters. How do you know that how many parameters affect wind? Because nobody knows the differential equation governing wind speed. We only have wind speed time series. So there is something called the nearest false neighbors. You take a ball and project it to 2 dimensions. You put a torch light and make a shadow. You project a ball, 3-dimensional ball in the wall. Then you get a shadow. The shadow is like a circular disc, but the opposite points may fall on the same. Here one point here. Say for example, if you make something like this is a ball. Here you have a wall. So you put a light from here. So here you have a shadow, like a disk shadow. So this point, and this point may fall on the same point, or this point, and this point. Maybe when you project it somewhere here, and here, it may be very close when you project it, but actually they are far apart, apart. So when you do this, these are false neighbors. Actually, it's not far. So from the original time series, you construct an attractor with the 2 dimension. Then you find the number of false neighbors. Maybe it will be high. When you increase it, the dimension, when you project into 3 dimensions, it may not be false neighbors. When you increase this, the number of false neighbors will decrease. It will keep on decreasing. Then it will level off. Usually, this is the technique people use to find the optimum delay. So here, somewhere, these values you can faithfully take, because at that kind of so this system is like an 8-dimensional system. This is from the Earth's magnetic field. The Earth's magnetic field in a way, are affected by 8 other parameters, the magnetic field of Earth, just by measuring it. I mean, what are the other parameters it is affecting? Like, I mean, it may be affected by the internal dynamics, in Earth's internal dynamics of Earth, and maybe also some parameters from the outer space. And anyway, it says that it will be affected by first value, second value. See here, the fraction is very high, the difference. So it will have at least 3 or 4 values, but thereafter the effect of other values may not be that significant. So just by looking at, you can get an idea that it is affected by so many other parameters. So you calculate here. So from the mutual information, we can get delay. And from this one, like, from here up to this much, we can take actually some value within this range. You can take as an embedded dimension. So you will get to know what is an embedded dimension. In the case of wind, actually, I mean, it's like a 10 minutes difference, like, I mean, then you get the embedded dimension around 10, and even if you take 8, it's okay, like, the fraction of fast neighbors has come down drastically, like, I mean, so the wind is affected by up to 6 or 12 parameters, like, more than that is not affected. So you'll get an idea that just by doing it, you get an idea that what are the number of other parameters affecting this wind speed fluctuation. You get a clear idea, like, so that itself is useful, like. So this is Earth magnetic field. See, Earth magnetic field. From that, you can construct the attractor by delay embedding. Now you can get an attractor. Then you will study these attractors, generally fractals. Fractals means it does not have a common as a usual conventional kind of geometry, like, Then you can calculate the fractal fractal dimension. There are different dimensions you can associate with one popularly used one is correlation dimension. So this is very popular one. I mean, in the package, I will show you that package. Tyson Package has got a tool. It's very easy to use. You don't need to know much, and you'll get a figure like this. You may have a plateau region, like, plateau region. So if you fit a line, you'll get an idea about the correlation dimension. So when the correlation dimension is small, it kind of given what you call information that the underlying dimension, underlying dynamics is low dimensional. That is very important, actually. If it is very high dimensional, it is of no use. Like, you may not predict it accurately or something. When I said for a stochastic time series, the dimension is almost infinite. But this one is, if the dimension is very high, also it may not be that useful. If it is low dimensional, it is useful. Here in this system, from this one, Earth magnetic field, if you analyze, there is a kind of low dimensional one. So that itself shows that it may not be random. Like, by just looking at, you didn't get any idea, like, whether it is fluctuating randomly, it is random features and all. But if you kind of, the analysis will give this kind of image. So I will show you how to do that. I mean, practically, like, I mean, instead of, I took a fictitious data and I took the first value. The first value may not be 1, it may be some other value. To know the position, I just put it as 1. So first value, second value. So this is a time series. You only this one. How do you get a delayed? So I can embed this into a 4-dimensional space. Here I have embedded it into a 4-dimensional. Then I took 2 as the delay, actually. So the first value, then delay 2. So it only third, then fifth, up to 4 dimensions. So this is a vector. This is a single point in the 4-dimensional space. So in the 4-dimensional space, it's a single point, 1 point. So you get another point. It's like, again, a single point in the 4-dimensional space. So you get a vector series like this. So when you have a vector, you can plot it. So this kind of embedding from this time series into 4-dimensional time series. So this is, this embedding will give, the topologically equivalent attractor of the original dynamics. For the original dynamics, we don't know the other parameters. But when you do that, when you plot this, you can faithfully connect it. So that is what the embedding. I think you got the idea, because concept is more important than other things. One of the best tool I have come across is this Tyson package. Developed by Holger Kans and Schreiber, and they developed this software. It's a very good software, but only problem is it's command-like thing. You can go to this, you can search with the Tyson. They have Windows executive binary files and Linux a binary, and also you can compile it. It's open source, free software, but very effective, very effective. But when I also encourage you to learn, if you want to do this kind of analysis, better to learn a Linux operating system, because Linux comes with a lot of tools and other tools which will make it very easy, actually. I mean, I know many people are a bit stuck to Windows, but I encourage you to use Windows these days, because these days using Windows is not that difficult. It's also similar, almost similar to this one. So this is a very good software. I will show you some of thing possibly. I will show some bit of demo also. Like, see, so this is a Lorentz differential equation. So this is a Lorentz system. I said the conversion equations. Like, now there's a 3-dimensional equation. So what are the 3 dimensions? What are the 3 dimensions? So this is the x. I mean, I integrated this differential equation. I got the x component. This is y component. This is z component, right? So I have, so I can plot this as a single point. So I get a single point somewhere around. So the next value, I get something like this. So then keep on. I joined all these points. So you get an attractor. This is the original attractor. So this is the original attractor. The original attractor is this one. Then what I did is I only took this value. I did not take these values. These 2 values I did not take. Okay, I only took this value. Then I found the mutual information. Then I took the mutual. Then I found it 1. Actually, I took the delay as 1. Then embedding dimension, I took it as 7. I mean, so you can embed it actually. I will show you how to do it, but it's not that difficult. You take the first value. Delay 1 means you take 7 and the difference of 1, 7 values. 7 values you take and plot it like this. Put it like this. Then delay 1 means the second. After 1, you take the next one. Like that, you can keep on do actually. So you get all the 7-dimensional system. Then I plotted this, the first versus, because it's a 7-dimensional system, you can't write up to 3 dimensions. You can have otherwise you cannot plot. So I just plotted this versus this. I mean, it's a projection into 2 dimensions. So the attractor was something like this. So that means the dimension is not good because it's just 1. So when it is too low, actual dimension is attractor is something like this. When it is too low, I mean, it's kind of what you call shrunken. Like, no, it may not reveal much of the idea. So then I increased the delays to 10 with the embedding 7. Then you see there is no difference, almost the same. Is it not beautiful? Like, I mean, just by looking at one component, without using these 2 components, you can get the attractor. You can construct the attractor. It's not that difficult also. Even if you don't have any software tool, etc., you can do this actually. What's the big thing about it? I mean, you get, and there is one more theorem also. If there is something called 2n plus 1, like, if the original system is 3, then 2n plus 1 dimension, if you take, it will faithfully reconstruct the original system. There is somebody has demonstrated that. This is a guiding principle, like, if but many times we do not know the exact n, but here we know it is 3. That's why it just took 7 as 1. So from one component, then embed into this one, then plot it, you get actually the original director. So from this one, actually, we can, I mean, even if this is the original system, but to get the original system, you need to know all the components, like, but many times we don't have the knowledge about all the components. From the one component, we can get it actually beautifully. I mean, this is from the theoretical one, because we already know what would be the exact one, because we generated from this differential equation. So this is how embedding. This is what guaranteed by the Tyson theorem. You can topologically get the original system. Like, you can even the values, if you take, the range is also almost similar. If you look at it, that's the beauty about this. Then some of the analysis we have done actually. So we have done some analysis with the geomagnetic horizontal field. That times is a bit older paper, and geomagnetic, yeah, it is 2002, sometime back, with the collaboration with Professor Renuka in the physics department at Kerala University. We have done it long back, and this one, and construct the attractor using this method of the geomagnetic field. You'll get a lot of physics data, I mean, the data from the physics, TEC, total electron content. This is also a lot of, there are a lot of work going in total electron content this time series, whether is it possible to model it, whether to predict it. Because even the space satellites, you know, if there is a huge, tremendous magnetic storm that might influence the function of a satellite, artificial satellites, like, you know, Apollo, I don't know the number, like one of the Apollo mission was failed because of the magnetic storm, like, you know. So these kind of thing you want to predict it, whether it's possible, kind of, is it possible? You may not be able to predict exactly with the present knowledge, but you get at least some hint, actually. Recently, we were working on wind speed. We have several publications, wind speed variation center. If you look at the wind speed, I mean, it looks like almost fluctuating. But if you can recently, this one, we've shown that this is low dimensional. We have proved or demonstrated that the fluctuation is low dimensional. And then this deterministic, there is a governing equation. Even though it looks like random, there is a rule working behind these fluctuations. And we show that it is chaotic. That is why it's like fluctuating. A chaotic is may look like imitate like it may imitate stochastic random fluctuation, but there is a rule. So we have shown in the terms of how accurate we can predict. Up to this much, we can very reasonably predict the wind speed. And wind speed prediction, I mean, there are three future horizon we want to look at it. For maintenance of the wind turbine and all, I mean, switching over from this one and all, you need to know very short-term prediction. Then kind of medium-term prediction, like that is also required. Long-term prediction is also required, actually. So there are three horizons to predict. But in the short-term prediction, this method, this is one good, people have started using machine learning techniques, artificial intelligence method and all. But this is a very simple technique, computationally highly efficient. I mean, but still the prediction is reasonably good. So we have several papers in this related to wind and published. I mean, the TEC also, there are a lot of papers actually on this. And just wanted to give a flavor what you can do with that. Even if you have, as Professor Shankar Raman has mentioned, he has generated data related to optics. And we have analyzed that kind of analysis. That also where we use the kind of analysis with these tools, actually. So wind prediction, you can reasonably you can do that, actually. So this is what I wanted to give. Maybe I just wanted to give a bit of demo, actually, because for freshers, I think the demo is more important than the for, actually. So I don't know whether is it visible now? Like, is it visible now?
Yes, sir.
Yes. Okay.
Yes.
Just to show how to do that, actually, there are. I mean, if you download, if you download Tyson, it has got a lot of softwares, actually. See, these are all for different purposes. I will show some time kind of thing. See, for example, I will just to show how to do this, actually. Okay. Let me check. Just a minute, why I wanted to show demo is that otherwise, I mean, we may think these are all very difficult. I mean, just wanted to show that doing this is not very difficult to get a feeling. That might encourage the youngster to work on that. I'll just to show, see the time series, actually. This is wind speed fluctuation time series, like, sorry. Okay, just a minute. Okay, so this is wind speed fluctuation. You have wind speed meter per second, the actual measurement of the wind speed. I mean, just to plot it, actually plot wind data. Like, I mean, I would also say that there is a software called the GNU plot. It's very useful for plotting. See how convenient it is to plot. If you look at the wind speed fluctuation, it's almost like random. I'll show one small part of it, actually, to get an idea. Like, so 1 to 1,000 values I'll plot. So to plot that also, this is very good. You don't have to do that. You just to plot it. So this is the fluctuation. Okay. So this is how it fluctuates. Now, see, this is how it fluctuates, the wind speed. Whether we can predict these kind of fluctuations or future values, that is what we are interested in. So this is the value, okay? So this is the value. Suppose if I want to convert this into embedding dimension, there is a in the Tyson package, there is something called delay. There is something called a delay. So if you want know how to use it, there you can give like a yet delay kind of. It will give all kinds of parameters. There are useful parameters as well as there are some parameters it will automatically take by the default one. So I want to put the delay, maybe shall I put it something like 20 or 10? I put a delay or I put maybe 20. I'll put a delay as 20. The value of delay is 20. I have explained what delay is. So embedding is, I just took as 8. Then I want to analyze this time series. Then if you put it, it will embed into this one. It has already done it actually. So I'll just show both the data. Like this is the wind speed data. Okay, this is the wind speed data. Then it has written the embedded one into this one actually. Just to show. See, it has embedded into, because I gave to embed this command into 8-dimensional space. 8-dimensional space. So it has embedded into 8 dimensions, this one. So, and all the values. So this you can plot it actually. You just plot the original time series we have seen. So I can plot the wind into delay. Maybe I can take first component versus second component. Okay. First component versus second component. This one versus this one. Okay. I can plot any. See, this is kind of attractive. So it shows kind of a structure within this. It may not be that completely random. So this is what we did actually. I just wanted to show this. Want to get a feeling that it's not that difficult. This package is very good. Just wanted to make sure you know this package. It's almost, a lot of things out there, like Lorentz system. There is a package. There is a command. You can generate the Lorentz system data, Bose counting dimension, correlation dimension. There is a one. There are a lot of things. Even want to make a surrogate data test, how to generate surrogate data, the command is there. So you only need to know the basic idea. Like, that is what I wanted to. Okay. Just wanted to. So this is how you do that actually. Next, I will go to networks. How do you convert it into network? So is it my my desktop, that PPT is visible? Like, is it visible now? Can somebody respond?
Yes, sir.
Yeah.
It is visible.
Okay. So now we want to analyze time series and convert it into a network actually. So this one, if you look at it, this is the original time series. Then we convert into a network. A network has got two entities. One is called a node. These called a node, and two nodes are connected by an edge. This is, mathematicians call it as a graph, and for others like a social scientists, they call it as a network. Like network analysis is very popular these days because many of us are friends in Facebook. Like we can construct a network of Facebook. If this is one person in Facebook and he is connected to another person in Facebook, because they are friends in the network. Like this is being analyzed in many different systems. Like a social scientists analyze this kind of network. It has got a lot of practical applications also. So network theory is very popular these days. Network analysis. This is not only about the social networks. Even there is something called a protein network. So because when they develop some medicine, some drug or something chemical, for maybe one part maybe be the cause for some particular thing. So you want to alter that site. So if you develop a drug and alter it, what happens is maybe connected to so many other parts. So when you alter one part, that may affect the healthier part also, some other part. So before developing it, you want to know this particular site is connected to so many, which are the other part it is connected to. So for that kind of thing also, they do this kind of network analysis. They call it as pathway analysis, and there are a lot of applications for this complex network. But here, I'll only be talking about how time series can be converted into network. One area people recently is using this kind of network is for the medical field, like medical field. For example, a person might have had a serious disease, something like a heart attack or hemorrhage or something like that. So they may get a treatment. After that, they might completely recover. But the psychological state will still persist on, like, even if might have recovered from your disease, you may still think that, oh, I am a patient. Any time in future also it can occur. If suppose you have had a heart attack or a hemorrhage or something. So thereafter, even if you have fully recovered, I mean, psychologically you might still have kind of feeling like you are a patient. I mean, they have analyzed these kind of patients and identified there are 4 types of people. Like, some people after recovery, they will fully back into life. They'll be happy, like, they don't think that they're still patients. So they will enjoy life. That is one category of people. Some people, they will recover after something. For 1 more year, they may suffer mentally. They may suffer mentally, or they may suffer psychologically about the disease he had. But after 1 year, they will recover. Mentally also, they will recover. That kind of people. Some people will never recover. They will keep on thinking that they are patients even after they have recovered. So there are 4 kinds of this one. So what some people have analyzed is they took the brain signal. They took the brain signal. They converted into this kind of network. Then they analyzed this one. For these 4 types of people, they have 4 different types of network. So they say by just analyzing this network, you can know what kind of the person he is, like, what category he belongs to. Because otherwise, if you look at this may not be very easy to get any information. It doesn't reveal much. Actually, it's very difficult to get any information from this time series. But from the network, it is much easier. So that is the one reason people started using this kind of thing. This is not the only reason. There are a lot of other applications. I would first say, what is a graph? A graph has got 2 entities. One is a node, and these are all nodes. Actually, these are all nodes. And the other thing is a line. Some network, the connection between 2 nodes, it is called it's called a edge, actually, or it's called a edge. Sometimes arrow may be meaningful. Sometimes arrow may not be meaningful. So here there is no arrow. Here this is a directed network. Say, for example, I consider you as my friend, but you don't consider me as a friend. So this is unidirectional. I consider you as a friend, but you don't consider me as a friend. Something like that, actually. One person may consider other as a friend, but the other person may not consider. So in that case, this direction may be useful. Otherwise, it's not useful. So this is what a network. Mathematicians, I would say that mathematicians call it as a network. Mathematicians call it as a network, but mathematicians call it as a graph, and the sociologists call it as a network. It's called a complex network analysis. There are a lot of work going on here. I mean, even computer network. I mean, applications are too many, like complex network analysis or social network analysis. A lot of analysis. Okay, I will introduce 3 types of 3 methods by which we can convert a time series into a network. This is one of the simplest method, visibility graph. So see the time series. First value is 0.87. Second value is 0.49. So this is a time series, right? This is a time series. It's a time series. Then you make a plot like this. So this is 0.87. This is the first value 0.87. Okay. This is first value 0.87. The second value 0.49. Third value 0.36, like that. Then based on visibility, so all these points are not. This is 0.87. This is the second 0.49. So each value in the time series is a node. Then whether this is connected to other one, if it is visible, you draw a straight line. If it is visible, there is an edge. Okay. So this is connected to this one. This is connected. So we can, it's visible in the sense through a straight line you can see this. But you can't see this actually, because this is not correct actually. Why? Because this is hiding. This is hiding. Like, then there is not connected. So then you can convert this into a network. This is a kind of network. You need not plot it like this. You can plot it like this also. Like, that way you can convert. I mean, you need not plot it the same way. Like, different way also you can plot it. So this is called a visibility graph. So people started using it also. There are a lot of applications for it. This is the first method. Like. And the most popular thing in physics, what people do is a recurrent network. There is something called the recurrence plot. Actually, by making recurrent plot, you can get some idea whether the given time series is deterministic or has got some kind of determinism also. I'll show one example. Like, okay, so this is a time series, right? As using embedding dimension, you can get an attractor. No, I have in nonlinear dimensions, you can get an attractor. I did not continuously draw the line between them. I just plot it as a plot. So, I mean, I plotted in the first 3 dimension. Like, so from the time series, you can get an embedding. Through embedding, you can get an attractor. So much we have talked already about using that embedding theorem. So once you that, so I mean, yeah, a portion of this I have plot as an enlarged one. This is a plot of this as an enlarged one. What they will do is they will take an epsilon value. The diameter of this circle is epsilon. So then put a circle. So whatever comes within the circle are connected actually. So this is connected to this, this is connected to this, this is connected to this. This is not connected to these nodes because this outside this. So like that for every point you draw a circle, whichever comes in this one, then you will convert it into a network. So this network is called recurrence network because it is generated from the recurrence plot. So there are a lot of papers on this. Many people in India also working here, working on this actually, which epsilon you have to fix and kind of thing. A lot of people, we are also working in this one to get, but it's still evolving in the sense you may not get all the features of this time series from this network, like particularly the dynamical quantities. Structural properties you can get, but the dynamical is still elusive for the analysis, like, so we are also trying to develop better method to get this. This is one area we are working. So this is called the recurrence network, like you can. Another area, something called symbolic dynamics. There are people working in this area. So this is a time series, right? So the first value is 0.75, next 0.3, 0.4, like that actually. Then what we'll do is we'll find the median of this value. Find the median. If the first value is above the median, then you put it as 1. If the second value is below the median, then put it as 0. Then each value is replaced by 0 and 1. If you convert it to binary series by just looking at whether it goes up or goes down, like goes down. So then you get a binary series. Then you take some part of it, maybe 10 quantity, and convert it into a decimal number. You might have got 64 as a number. Then you take from here to here, again 10 numbers, converted this to another number. Then you may get a decimal number. When you convert it, you will get to 60 or something. Then so these are the nodes. Then this is connected to this, this is connected to this. By adjacency makes the connection. Like when you do that, you get a network. This is called a dynamical approach to construct network. And people started using this network. I mean, there are a lot of papers. I can share some of the papers related to this. For example, this is also a good paper to start with. I mean, gives all the methodology and all. And so what they say that by just analyzing this network, you can get many idea about the original time series. This is another method actually. And there are other methods like original time series you make into segments, like, this is this pink color. This one is the original time series, but you cut this into one segment. Okay, that segment you consider it as a node. I mean, we call it as a node, but actually it is a segment. So this is another segment. You call it as a node. I mean, this node means that's the segment. Then another node, all this one. So we find the correlation between this and this. If the correlation is above a certain quantity, like 0.8, then they are connected. Like then again, this segment, this segment, you take the correlation is not above 8, there is no 8. So whichever the correlation is high, you get. So you will get a network. This also people started using. And some people use instead of correlation mutual information. I said what is mutual information in the biological science, like that. I mean, in the medical field and all, they construct this usually usually with the mutual information, like so when you analyze this network, you will get to know many things of this. I mean, they use this as a diagnostic tool also. Suppose if you have just a heart signal, like heart pressure or something, if you time series, just by measuring the heart pressure, and you get a time series converted to this kind of segment. So you know how much is the time for one laptop. That much you make it as one segment. You take other segment. If you analyze this kind of correlation, you network. If the network property for the normal people are of one category, abnormal, if there is some kind of abnormalities, the network will behave differently. So when people have published papers that you can diagnose a patient just by using this. Well, these are a really useful thing, right? Is it not useful? Because you don't require a medical doctor to make an initial assessment. It may not be perfect. When further you may have to consult a medical doctor for clinical assessment. But before the clinical assessment, as an initial analysis, you can also, suppose if you write a code, every software code you can convert into hardware, right? Using EEPROM or something. You develop a handheld device. I mean, then you put this. You can measure these values and get. You can diagnose a person without much medical science. So these are the advantages. There is a mutual quality. I mean, there are other methods also. I'm not going into all the methods. I just wanted to convey a feeling, like, what this area is about, how we can do that. I included the demo for the freshers. I mean, I did not talk much about the what you call the other things, because I mean, this is more of like, to get you motivated for the freshers. I mean, if you come up, I mean, you might have had already, if you are working in laboratory or in real world, you might have come across some kind of a time series. So this will be very easy for you to kind of do this. So I just wanted to get a flavor about time series analysis. Like, this time series network is an evolving area. Like, it's a bit of evolving. Okay, thank you very much.